We are in love with solar cooling, and the reason is because, as you know, solar photovoltaics is the cheapest form of electricity nowadays. This is a wonderful news. And in combination with cooling, it is a wonderful thing because if you think that 1 square meter panel, PV panel, 1 square meter is able to produce or to deliver enough energy to produce 18 kg ice in 1 day, then you can see how powerful this is. So 1 square meter is not a big surface, and during the whole day, the solar irradiance that you obtain is enough to produce 18 kg ice. With 18 kg ice, you can cool down 50-liter milk from 35 degrees to 4 degrees. So it's a wonderful solution, very powerful and efficient. So every square meter of PV panel, you can cool down 50 liters of milk. How to do this? The PV panels are combined with a cooling technology, which is obvious. And in this case, we use heat pumps. So conventional heat pumps, similar to what you have at your car or your AC system, or also the milk tanks work like this. And I will let you know in some slides later on what is the COP, but I advanced it already to you. A COP is the coefficient of performance, and this is the relationship between the cooling energy you get and the electricity you invest. And to produce ice at 30 degrees ambient temperature, a heat pump has a COP of 2. This means you get the double amount of energy that you electricity, and this means if you multiply the COP by the efficiency of a PV panel working at a tropical temperature, around 17%, then we can talk about 34% conversion factor. This means 34% of the solar radiation is converted into cooling energy. So this is really amazing. The combination of PV with a heat pump it makes solar cooling very efficient. So 1/3 of the solar radiation is converted into cooling energy, is converted into ice or any other form of cooling. Now let's have a look to why do we want to cool down milk. The reason here is because milk is really perishable. Milk spoils very quickly, as you might know, and depending what is the start quality, because you cannot make the quality of milk better by cooling. You just can't preserve the quality of milk by reducing the temperature. So what you can see here is a curve where you see what's happened to the bacteria in the milk if you don't cool it down over the time. So you see milk has 37 degrees after milking, and at this temperature, you can see here how exponential the bacteria growth takes place. And if we take into consideration here in Germany, the limits on bacteria count on milk that you can sell, then we are talking here about 100,000 coliformin units per milliliter, and this will be already achieved after 3 hours after milking. So you see it is quite fast. So we need to cool down milk very fast after milking. A challenge that we have in rural areas is that there are two challenges. The first one is obvious. You don't have often milk cooling directly on the farm, so you cannot cool down your milk right after milking. The second challenge is that the hygiene conditions are worse than at bigger farms, so that the starting quality of the milk is worse from the beginning. Let me show here the second curve. So what we find in rural areas for milk quality is around this 300,000, 400,000 coliformin unit bacteria per milliliter milk. And then the whole process of spoilage happens even faster. This is obvious. So the worse you start, the faster it happens. So here we can talk about the spoilage between 3, 4, 5 hours after after milking, you cannot process anymore the milk. The milk gets sour, and you cannot even pasteurize it, so that is not anymore useful and would be rejected. So this is the reason of why having milk cooling as soon as possible and as fast as possible. Then let's have a look to what's happened if we cool down the milk at 20 degrees. 20 degrees, you see, it slows down a lot the spoilage process, so the bacteria growth happens slower. Even better is to cool down at 15 degrees. So you can see cooling down the milk at 15 degrees already helps a lot to transport the milk during the day. So here, depending on the limits that your dairy plant has, then you can have around 8 to 10 hours to bring the milk to the processing plant. This means 15 degrees is quite a good temperature for daily transportation. It depends, of course, if you can keep also this temperature all over the transport. 10 degrees is wonderful then to keep the milk all over the day. As you can see here, the increase of bacteria keeps relatively low. But as you know, 4 degrees is the best temperature to make sure that bacteria growth is not happening up to 2 days. As you know, milk tanks normally also in rural areas, they are working at 4 degrees. It is not always necessary to keep this temperature, but the reason why this is done is also because you want to assure that later on between milk collecting center and dairy plant during the transport that the milk doesn't go into a dangerous temperature level, so to say. But I just wanted to let you know, depending on the time you need, you will select one or the other milk temperature, milk cooling temperature. Let's have here an example. These are measurements that we have done ourselves in rural areas. You do milking here in a milk can. Here the red curve will be you don't cool it down. So after 3 hours, you go here from 8,000 coliforming units to almost 100,000 within 2 hours. So you see this happens very, very quickly. These are the how the bacteria count is done by colonies, and then you can see what's happened to milk in just 2 hours. If you cool down the milk here to 15 degrees, you see the bacteria growth is very limited. So it is quite essential to do to have good hygiene conditions at farm level, and second, to do milk cooling right after milking, so to say. This helps a lot to preserve the quality. If there is no other possibility, then the transport of milk has to be done very quickly to a place where a milk tank is available. So cooling with solar energy, okay, how can we do this? Which options do we have? There are different refrigeration systems. As we are going to see here, you might have heard about evaporative cooling. So this is the most cost-efficient way of cooling down products used by the evaporation of water. So this is quite useful for cold rooms, for example, that are run at a temperature no lower than 20 degrees or 17 degrees. Evaporative cooling is a good option for that. Solar cooling in the past was related here to these technologies that was used with thermal modules. So I'm talking about absorption and absorption cooling. So this is solar thermal cooling. So this is also a technology that is available. But today I'm talking with you about solar cooling with photovoltaics panels, and we are talking about vapor compression heat pumps. It's just for you to know, we are here, we are talking about this technology. There are other ways of doing solar cooling, other kind of technologies, but we are very focused on PV with heat pumps. What is the reason? The reason is that the cost of PV panels have decreased a lot in the last years. And the heat pumps are available everywhere. As I told you, air conditioners, fridges, refrigeration systems for cooling, milk tanks, they all run on heat pumps. And that's the reason why we go for this technology, because it's just at the end of the day combining existing components that are available. Okay, so now it's getting more and more technical. I hope you are ready. Probably we have here, or I heard before, I think Maria is a refrigeration expert, so probably she knows all of this. But I think it's very important to understand how a vapor compression heat pump work. A vapor compression heat pump sounds like very complicated, but it's quite easy. What is a vapor compression heat pump? It is actually a cooling system, okay? So it is a fridge or a refrigerator is a vapor compression heat pump. An air conditioning system is also a vapor compression heat pump. Also, the AC system from your car has also a vapor compression heat pump. So if we figure out the words here, vapor compression heat pumps, then we are quite sure we might have vapor somewhere. So this is the refrigerant, the gas. We might have compression somewhere. So we have a compressor, right? And if we have a look here to the term heat pump, so it has to be something that is pumping heat from one place to other, right? So this is the most important we want to understand today. Let's have a look to the different components. So we have a compressor. The compressor is compressing a refrigerant. Then at some time we have a condenser that is outside. So this is, you know, in your air conditioner is the fan that you find outside that is releasing hot air. Then you have at somewhere an expansion valve. And you have at somewhere an evaporator. This evaporator is what is producing or releasing the cooling energy, or better said, is extracting the heat. Yeah. Okay. And here the evaporator, this is where we have the milk tank. So the evaporator is somehow in contact with the metal of the milk tank, with the stainless steel in the inside walls. Okay. And then we have a thermodynamic cycle, so to say, that is somewhere using electrical power at the compressor. So we have here the compressor, we are consuming electrical energy, right? Then we are compressing the gas, the refrigerant. Then we are rejecting heat, as you can see here. This is happening here in the condenser. Then we are expanding the gas and we are extracting heat here at the evaporator. So we are extracting the heat of the milk, so to say. And then coming back to the compressor. The heat extracted is what we call cooling energy, but cooling energy doesn't exist itself. So we just use it so that we can imagine it a little bit, but what we are doing is we are extracting heat. So you can see here we're extracting heat from the milk through the evaporator, and we are releasing heat to the condenser, through the condenser to the ambient. Yeah. So this is how we are pumping heat. You see? So we use electricity power, mechanical energy to pump energy from the milk to the outside. Okay. Now the question is, how is this happening at all? And in order to understand this, I have here something that is like a pressurized bottle, okay? And this is going to be our compressor today, just to understand how this is working. And now imagine we are having an air conditioner so that we can imagine it better. So the air conditioner and the milk tank work in a very similar way, but the air conditioner we can imagine better. So imagine we have outside 40 degrees ambient temperature, and we want to cool down our room here at 20 degrees, just to feel comfortable. Okay, so imagine we have the compressor outside, and we are taking air from the room at 20 degrees, and now imagine our refrigerant is air. So it is not a gas, it is just air that we are compressing. So now we are investing mechanical energy right, to compress the air. Yeah. So we are investing the electricity to create pressure, right? So what is happening when we create pressure? So it's have to work always more and more. Yeah. What is happening when we are uh, creating this pressure? The pressure increase and also the temperature goes higher, right? Okay, if the temperature is going higher, we will be at the beginning 20 degrees, 30 degrees, 40 degrees, and then we keep on making more and more pressure. We let the compressor work until we achieve 60 degrees. So we have achieved 60 degrees. So now what we have here is air at 60 degrees and under pressure. Okay, we have air at 60 degrees under pressure. Now what we do is we go to the outside and we are at the ambient. The ambient temperature has 40 degrees, right? And we have here 60 degrees. So we are releasing the heat. We are cooling down this air with the ambient, right? So our air here is going down to ambient temperature, to 40 degrees. And this warm air is what we experience at the condenser, at the fan that is outside. Okay, so compressor made us possible to get high pressure and high temperature, and now the ambient was used to cool down the air here in this pressurized bottle. Okay, now what do we have? We have pressurized air at 40 degrees, ambient temperature. So now what we can do is we go to the expansion valve, which is here, in my case, this button, and then, so I don't know if you can hear, so I expand the air. What's happened when I expand the air? Then the pressure drops, and what's happened to the temperature? The temperature also drops. How is it going to drop now? If we went from 60 degrees to 40 degrees, now we will go from 40 degrees to theoretically 20 degrees. This is in theory. Normally we have losses and so on. But the air here at 20 degrees coming out of the bottle inside our cold room is then releasing the cooling energy. And if you can imagine this cold air, the cooling energy of this cold air is actually coming from the ambient. And the compressor is just helping us to get the different pressure levels, right? Pressure and temperature levels. So the compressor is not producing cooling energy. The compressor is helping us to get to the two different pressure levels and temperature levels so that we can take cooling energy from the ambient and release it in our room or in our milk tank. The other way around, we extract heat from the milk or from our room and reject it to the ambient. Are there any questions here at this point on having a closer look on heat pumps? Then I will say we move forward. So now we are aware of the components that a heat pump has. So we have a compressor, we have a condenser, we have an evaporator, and we have an expansion valve. And we have, of course, the refrigerant inside the heat pump. Okay, let's move forward. So how do we calculate the efficiency of a heat pump? The efficiency of a refrigeration system is measured by the coefficient of performance, COP. So we don't really talk about efficiency. Why? Because the compressor has an efficiency to compress air, but the heat pump is not related to the efficiency of the compressor directly, because it is related on how well this heat pump is able to pump the heat. And this is related to the ambient temperature also and to the cooling temperature, because this is related to the two different pressure levels that we have to achieve. So the COP, the coefficient of performance, is the relationship between cooling power, so the cooling energy we get from the system, or the amount of heat that is extracted from the milk, divided by the electrical power. So how much do we get in comparison to how much do we invest? Yeah. And I can tell you the COP can be higher than 1 and is normally also higher than 1. So we are able to pump more cooling energy than the electricity that we invest into the cooling system. And this COP depends on the ambient temperature and on the cooling temperature. And this relationship was discovered by engineer Carnot in 1824 in France, and he discovered what is the maximum COP that a heat pump can deliver working at two different temperature levels, so warm temperature and cold temperature. You see here the equation. We call here this COP, this is the ideal COP, or we call it also Carnot COP. So this is the maximum COP that a heat pump can have operating at two different temperature levels. The COP of our milk tank, of our real system, it is not going to be as high as the Carnot, as the ideal COP, but it is going to be related to it. And that's why we talk here about an ideality factor, alpha, which is multiplied by the COP ideal. So there is a way of calculating the COP that your milk tank will have. Based on this, I can tell you that the ideality factor is typically around 25% of the Carnot COP. Or you can, of course, measure the COP, but this is something that normally is done at laboratory level. But it is important for you to know how to estimate more or less the COP of your milk tank, because when you know the COP of your milk tank, then you can know, based on the amount of milk that you are cooling down, you can know how much electricity you will consume, right? And the electricity you will consume is related to the amount of PV panels and batteries that you need. That's why for solar cooling systems, it is very essential to make a estimation of the coefficient of performance of the cooling system before we design the solar system for that solution. So let's have a look here, just for you to have seen where the values are. If we consider a conventional milk tank, and you remember here the COP is the relationship between cooling and electricity, the Carnot, the ideal COP would be, if we are cooling down milk at 4 degrees and we have ambient temperature of 20 degrees, then we have an ideal COP of 17. This means if the heat pump will be perfect, then the maximum cooling energy we will get is 17 watts per watt of electricity. So we invest 1 kilowatt and we get 17 kilowatt of cooling power. At 30 degrees, it is not 17, it is only 10, and at 40 degrees is 7. This is the ideal COP. The real COP, it is less than this. As I mentioned, it is about 25% of this. And then we have COPs around 2.6 for 20 degrees, 2.1 for 30 degrees ambient temperature, and 1.8 for 40 degrees ambient temperature. So even though the milk tank is operating at 40 degrees ambient temperature, we have a COP of 1.8. This means every kilowatt hour we invest in, so every kilowatt hour we invest in electricity, so the compressor consumes 1 kilowatt hour, for example, then we are delivering 1.8 kilowatt hour cooling to our milk. And this is, of course, very interesting because you always need to calculate the thermal power, so the energy you need to cool down your milk, and then you calculate with the COP. So you divide the thermal power by your COP, and then you get the electricity energy that you need to consider. And based on this, you can design your solar system. So this is a very, very important process that needs to be done while designing a solar power milk tank. The reason is here, by the way, if you have a milk tank, a solar power milk tank, cooling down 2,000 liter milk per day at a location, and then you have a 13 solar system. If you have the same system in another location that has a little higher ambient temperature, then the electricity consumption will be higher, quite considerable higher, because this is very sensitive to ambient temperature. So for solar power cooling systems, the solar radiation is not the most important. The ambient temperature of the location is the most important, yeah? And also, of course, the amount of milk that you are cooling down per day. So ambient temperature takes here for milk cooling systems a very important role. Let's have a look how a milk tank works. So a milk tank has a heat pump somewhere, yeah? The condensers are normally outside of the room. Then we have an agitator. So we have a mixing system for two reasons. The milk coagulates if you don't move it continuously. Yeah, if you don't move it for more than 2-3 hours, then it starts to get layers of fat on the top of milk. So we have to keep on moving it. This consumes also electricity. And also for the milk cooling to happen faster, it is better if you move the milk, because then the milk cooling curve happens faster. So the agitator is very essential in a milk tank, then the cooling system, and then of course we have a control system, a manhole to clean the tank. As you saw before, hygiene conditions are very important here, and that's why the cleaning of a milk tank is also essential. Without hygiene, without cleaning, you better don't do anything, because milk cooling cannot make the milk quality better. So if you have a milk tank that is not clean enough, it doesn't matter how well the cooling is, how low the temperature is, your milk quality will be bad anyways. So cleaning properly milk tanks is very important. That's why we need to have high quality milk tanks made of stainless steels without corners, and to have the possibility to be cleaned every day very well. There are different types of milk cooling tanks. There are the open milk tanks, vertical and horizontal, and then there are the closed milk tanks, also in horizontal and vertical. So I guess you have seen this already often. And if we talk about the different milk cooling methods, there are also different types of how to cool down the milk. And I would like to talk to you about 3 different ones. So the first one is the direct cooling. The direct cooling. What means direct cooling? Direct cooling means we are cooling down milk and our compressor is working and is consuming electricity at the same time. So it is direct cooling. We consume electricity, we cool down the milk. We'll have a look in the next slides. But there is also the possibility of having indirect cooling. What does it mean? It means first we produce ice, for example. We are talking here about an ice storage, or we cool down water, and then with this cold water or with the energy stored in the ice, we cool down the milk. So this will be the case of having an ice bank, an ice storage system. So imagine a cooling device that is producing ice all over the day. And then once you have to do your milking very, very, very early in the morning, then you use this cold water to cool down your milk. So this is here, the electricity consumption doesn't happen at the same time of your milk cooling, right? Because you are producing ice all over the day, but milk cooling you are only doing early in the morning. That's why we call it indirect cooling. Then with the ice storage or water storage, can be also used For pre-cooling, pre-cooling means we cool down the milk before entering the milk tank. Well, we have a slide for this in a minute. I just have seen there is a question. Perhaps we can answer it in the meantime. So the question is from Patrick. Does the type of material used for the milk tank can have a direct effect on the efficiency of the heat pump, considering that different materials have different thermal conductivities? Yes. Normally, anyways, you are not going to find what milk tanks that are not made of stainless steel, because stainless steel is a very hygienic material. So hygiene is very important. And then it is important that the conductivity, as you said, is given. So the evaporator has to be in touch with the inner wall of the milk tank, and it has to have a high surface. Then the surface between milk and methyl is bigger, and you can cool down your milk better, faster, and more efficient. So yes, heat transfer is very, very important for heat pumps, because if the heat transfer is not given, then the evaporator temperature has to go lower and lower, and then your efficiency is lower. Yeah. I hope that answered the question. And now I would like to go deeper into the technology of milk tank. So let's have a look here to a direct cooling milk tank. Direct cooling milk tank. This is what we are talking about. We are cooling down the milk inside the milk tank. The evaporator is, as I said, in touch with the inner wall of the milk tank, right? So you can see it here, the evaporator, okay? And then you put your milk there, and you start your compressor, you are cooling. Yeah, that's all. So the refrigerant is going inside the milk tank, okay, to the evaporator. You cool down and you consume energy. Normally here we have quite big compressors, and direct cooling, in fact, is only done for small scale milk tanks. So more than 10,000 liters, then you have to go for indirect cooling, because otherwise your compressors have to get huge. But this is the state of the art. Normally in our milk bulking groups in Malawi, we have direct cooling milk tanks. So you have your cooling tank and your cooling unit together with the milk tank. Okay, let's have a look to the indirect cooling with ice storage. Here you see the heat pump is connected to a ice storage, yeah, to a machine that is producing ice. And then you have water and ice, and with the cold water you have an external water pump, and then with this water you are cooling down the tank. As you see, you are spraying water to the tank. This has a very nice advantage. The advantage is you can keep your compressors producing ice all over the day. So the compressor has to be smaller in comparison to the direct cooling solution, because the compressors are working for longer time, producing the ice. And then once you need milk cooling for 3-4 hours per day, then you just turn on the pump, but the compressors could be even off, because the cooling energy is coming from the ice. This has also an advantage for solar energy, because if you can produce this ice during solar radiation hours, then you don't need an electrical battery, right? So it is very interesting. Ice storage is good for milk because you can, so to say, reduce the size of the compressors, and this reduce also the investment cost. And it is also good for solar power systems, because then the energy consumption can also take place all over the day when solar radiation is available. Okay, and then the pre-cooling system, it is like you have, in this case, the milk tank, and then you are cooling down your milk before entering the milk tank, and this is done with cold water. This cold water can come from an ice storage, yeah. This is very interesting for systems where the milk really needs to be cooled down very, very fast, or where you are using an ice storage, but you don't want to get fully rid of your milk tank. Yeah. So this is just a decision of the milk collecting facility, yeah, or the dairy plant. Okay, so this is the pre-cooling. So the milk is cooled down before entering the tank with a heat exchanger, so a plate heat exchanger. Yeah, which have cold water and milk. You are cooling them down before going inside the milk tank. The advantage of these pre-cooling systems is that when you are using a plate heat exchanger, then you have a lot of surface to exchange the heat or the cooling energy between the cold water and the milk. So the milk is cooled down here very quickly. We are talking about around, it's in fact instant cooling. So we are talking about 5 minutes, 10 minutes to cool down the milk, depending on the final temperature you want to have here. Imagine you have a milk bulking group that is receiving milk from farmers that are quite far away. So when the farmers are arriving to your milk bulking group, you need to cool down the milk very quickly, because you cannot afford having a slow milk cooling curve of another 3 hours. And in this case, if you installed a pre-cooling system, then you can cool down the milk at arriving the milk bulking group from 30 degrees, because during transport the milk is also getting colder, from 30 degrees to 10 degrees very quickly. And this is the most critical range of temperature. And then you go inside your tank with 10 degrees, and then from 10 degrees to 4 degrees it is done here in the tank in a longer period. But the critical cooling part from 30 degrees to 10 degrees, it's done in 10 minutes. And this is very important for some places. But it's not the only reason of doing pre-cooling. Another reason is, as I said, to have an ice storage system so that your compressors here don't have to get huge, right? So you have better an ice bank, an ice storage system producing ice all over the day, so that this amount of cooling energy is available. Because imagine how much energy it consumes to cool down 2,000-liter milk within 3 hours. It's a huge energy. You also need to have a very powerful grid if you are connected to the grid, right? So this is the balance always for milk cooling. It's not only what we discuss about cooling temperature and cooling speed, but also regarding the electricity power that you consume out of your compressors. And here in this next slide, we have a typical milk cooling curve, just for you to see, okay, normally, milk tank needs around 3 to 4 hours to cool down the milk to 4 degrees. And it is critical, this first phase, that we decrease the temperature as soon as possible in less than 1 hour to below 25 degrees. That's, so to say, where the bacteria growth is at highest. Yeah, so this is something that has to be somehow logged, so that you can assure that the milk quality preservation is taking place. How to calculate the cooling load of a milk tank? So I talked before about the um, about the electricity consumption. I talked before about thermal energy, right? So here we are talking about thermal energy and electricity energy, right? So electrical energy. So first we need to know what is the thermal energy. We call it cooling load. So it's the energy we need to cool down the milk. Then we have the COP in the middle, and with this we can calculate the electricity energy that we need, right? The electricity, the power and the daily energy consumption. To calculate the cooling load, the energy we need to cool down the milk, there is a very simple equation. You see it here. The Energy, we need to cool down the milk, Q milk in watt hour. So this is really energy. It is not power, it is energy. It is equal to the volume of milk that we want to cool down in liter, multiplied by the heat capacity of milk, which is around 1.1 watt hour per liter and degree, multiplied by the delta T. The delta T is, in this case, 45 degrees is our milk, and we want to cool it down to 4 degrees, for example. So the difference between 35 degrees and 4, yeah, in this case, 31 degrees is what we will write here. So if we have, for example, 2000 liters, then it will be 2000 liters times 1.1 times 31 degrees. You will get the amount of watt hour that you need to cool down this milk. Then we need to figure out, okay, how many compressors do we need and so on. Then you will just see in the data sheet of the cooling system which is the right milk cooling tank that you need. But if we want to calculate the amount of power that our compressors will consume, then we need to consider that this milk cooling is happening in 2-3 hours. So the power of the compressors will be high. And this is the equation helping us to know what is the maximum cooling power that our milk tank has to be able to deliver. Because if a milk tank has a high volume but is not able to cool down this amount of milk in the time that you require, then it's not going to help you. And here you need to consider that milk tanks manufacturers, they provide different cooling units models for the same volume of tank. And this depends if you are doing 2 milkings per day, 1 milking per day, or you are doing 4 milkings along 4 days. So if you are doing 2 milkings per day, your cooling units are smaller than when you are doing only 1 milking per day. Why? Because in 1 milking per day, you are filling up the milk tank at once, right? In 2 milkings per day, you are having half in the morning and half in the evening, or 60% in the morning and 40% in the evening. So this is also important to select the right cooling unit for a certain volume of milk tank. So I hope that's clear. The design of an ice bank is also quite easy. If you are designing an ice storage system for indirect cooling, then you need to know how much thermal energy you need. What is the cooling load of the milk? This we calculated before, right? And you divide this by the latent heat of water, which is 92.7 watt hour per kg. Based on this equation, you get the size of your ice bank. So for example, I can tell you every 50 liter milk, yeah, you need around 20 kg ice. So this you will be able to calculate yourself with these equations, and then you know the size of your ice storage. So you know how much ice you need to produce per day. And based on this, because the ice forming duration can be 24 hours, or perhaps you want to have it only 12 hours during the day, then based on this, you know how big your compressors need to be, and you can select this technology from the supplier. So that everything is in balance. The energy you need for cooling down your milk is in balance with the energy that you were able to produce and store here in an ice bank. By the way, this is how an ice bank looks like, an ice storage. So you have here the evaporator tubes, and this is everything immersed in water. So you have ice, water, ice, water, ice, water, and then you take the cold water, which is normally at 2 degrees, to cool down your milk, and then warm water is coming back here to the ice storage. Okay, so now it's getting interesting. We have talked about the possibility of having a milk tank, of course, yeah, for direct cooling. We have talked about the possibility of using an ice bank for doing indirect cooling. So store first the energy in ice and then cooling down the milk. So that's an option. Then we have here our grid. So normally you might be connected to the grid. Because the grid is not always reliable, then we have a genset, a diesel genset there. And if we want to use solar energy for this, then we need, of course, the PV panels. We need a hybrid inverter, and we might need also electrical batteries. So you have here everything, all components you will need for a solar milk cooling system. Yeah. And now the question is, which configuration is the best for us? And we have here described 5 different configurations that are interesting to be to analyze, so to say. The first one, and this is a very important question, is before you start introducing solar energy to your milk cooling system, you need to figure out if your milk cooling system is efficient. So this is the first step. You need to analyze the efficiency of your milk tank before investing on solar, because it is better to replace the cooling unit than to put in solar, because a new cooling unit could decrease the amount of energy that you need, so could decrease already a lot your energy expenses. So efficiency is always better than renewable energy, right? So first, efficient appliances. Second, integration of renewable energy. So that's the first configuration. The second one is to use PV in combination with an ice bank. We will have a look to it. There is one slide for each configuration. Then the third one is PV and electrical batteries. The fourth one is PV and batteries and no genset. And the fifth one is PV plus batteries, no grid, no genset, fully off grid. So let's have a look to the 5 different configurations. The first configuration is the one about talking efficiency. It is very important to analyze if the COP of the milk tank is good enough. Because if the COP of the milk tank is not good enough, what you are doing is you are consuming more electricity than what you are supposed to consume for the amount of milk that you are consuming. For this, there are simple methods to do it. For example, logging the electricity that you consume all over a couple of days and measuring the amount of milk that you have cooled down in the same period of time. Then you can calculate the thermal energy and the electricity consumption you have also. You divide it and then you get the COP. And based on the equations we have shown before for the COP, then you can say if your milk tank is efficient or not, especially if you are also able to compare it to other milk tanks in the region. Second, very important aspect is the refrigerant that this milk tank is using. I guess you are aware about the importance of using refrigerants that are climate friendly. So you have here CFCs, HFCs, refrigerants, and other technologies that had come into place. You remember about the ozone layer issue that we had a long time ago, and now the problem is that most of the refrigerants that are used for milk tanks, they are not climate friendly. They have a global warming potential. This means every time you lose the refrigerant, you lose the gas out of the system, you are causing greenhouse emissions. And based on the latest studies, these greenhouse emissions at the refrigeration sector are 1/3, or so to say, of the total emissions of the refrigeration sector. 1/3 is related to the refrigerant, and 2/3 is related to the energy consumption. With solar energy, we only address this part of the emissions. With climate-friendly refrigerants, we address the other part of the emissions of the refrigeration sector at the moment. And this is very important in future, in the next years. You will see, and we are seeing this already this year in 2024, that the refrigerants that are not climate friendly, they are getting very expensive. The reason is because the use of them is not anymore welcome, so to say, and you have to always double check not only the refrigerant that you have, but also if you are losing refrigerant in your tank. So some milk bulking groups have milk tanks that um, lose refrigerant every year, for example, and they have to be replaced by new refrigerant and so on. And this refrigerant is coming to the atmosphere. And this is producing greenhouse emissions. This is not sustainable. And that's why it's very important to address this electricity efficiency and to use a refrigerant that is climate friendly, that has a low global warming potential. The refrigerants that have a low global warming potential are at the moment Air 600 and Air 290, isobutane and propane. For milk tanks, small milk tanks, they are at the moment not yet available, only for larger systems. So at the moment, we still need to live with refrigerants that are not very climate friendly, but are also not too bad, like Air 134A, Air 32, and so on. Those refrigerants are sometimes described as green refrigerants. They are not perfect, but they are not too bad. But what we have to take into consideration is that we don't need to replace gas. So if one milk tank is losing gas, this really needs to be replaced or repaired, but not just adding gas into the system, because this will cause greenhouse emissions, as I said. So this is the first step before going into renewable energy, to having a look to the efficiency and the refrigerant use. Configuration 2 is, let's not use electrical batteries, let's use ice banks. And in this case, if you have a look here to this diagram, the milk cooling energy is consumed early in the morning, sometimes even before sunrise. This means we don't have solar energy available at this time. So you see this peak of energy consumed. And this energy, to cover this energy, we need to use an ice bank if we are not using electrical batteries. So during the day, the ice bank is running. You see here, this is the PV power, and this is the electricity consumption of the ice bank. Then we produce here ice during the day, and then once we need to cool down the milk, then we transfer the cold water to the milk tank, and then we can cool down milk with solar energy through the ice that was produced by solar energy. Okay, this is a very nice solution. We don't need electrical batteries. We still keep the grid because in case of one day that the solar radiation was low, or the amount of milk that has to be cooled down was higher, then you always have the grid. And in case the grid is not available, you might always have the genset there, but you can imagine the amount of energy expenses that you have decreases considerable. So you have much less energy consumption from the grid, and you have much less diesel consumption from your genset. The balance we have always to find through the design. So normally, to reduce the energy consumption of the grid and the genset to zero, it is quite expensive. So it is better just to decrease this energy consumption to, so to say, only 10% of what you had before. Here we talk about energy expenses decrease of 90%. So this is like the solar fraction. And this is always a balance between the business model and the investment cost of the solar system. The investment here are the PV panels, the inverter, and probably also the ice bank. And the income generation is the savings on electricity consumption and the savings on diesel. And the business model is what is going to be analyzed on our third webinar given by Dr. Badelt. Okay, so this is the configuration number 2. We have ice bank, we don't have electrical batteries. The third configuration is to say we don't have ice bank, we better use electrical batteries. The electrical batteries are also connected to the hybrid inverter, and this configuration is very cost efficient when you have a solar fraction of around 80%. It means 80% of the electricity consumption of the milk tank is covered by solar directly or by solar through the batteries. Here, the PV power is saved into the batteries until the milk tank is on, and then you transfer the electricity to the milk tank. Here, this inverter needs to be a little bit oversized than in the previous case. Why? Because the compressor is consuming a lot of energy, so a lot of power, so to say. So if you want to be able to deliver this power out of solar energy and through the batteries, the inverter needs to be designed accordingly to be able to deliver this energy. Yeah, not only this energy, this energy peak, so the power. Okay, here we still have our grid and our genset. So here we expect a reduction of energy expenses of 80% more or less. This makes the investment cost quite efficient and low, because we are not trying to cover all situations where we have a very rainy day, where we have one day like a lot of milk and so on. These days we don't really want to cover fully. Yeah, and that's why the solar fraction around 80 can be also 90%. This is a economical question. Okay, so now let's go to configuration 4. In the configuration 4, we really want to get rid of the genset. Why? Because the genset is, especially in Malawi, one of the most expensive component of a milk tank or of a milk bulking group, for 2 reasons. The first reason is diesel cost is very expensive. The maintenance of the gensets is also quite expensive. And the grid, the electricity from the grid is not very expensive in Malawi. This means normally the highest energy expenses comes from the diesel generator. But this depends a lot on the site. There are regions that have more power shedding, yeah, and other ones have less power cuts or power shedding. So depending on this, you will use the configuration 4 instead of the configuration 3. Here, the solar components are bigger, so you have more PV panels, you have more batteries, and then you get to a solar fraction on 90%, and you have 2 batteries. You have one primary battery for the normal daily consumption, and you have a second battery bank that is reserved for in case that the grid is not there, solar energy is not available, and the primary batteries are empty. Then you have the second batteries that are there as a backup. So they are there always ready to substitute the role of the diesel generator. And this is also an economical question. Does it worth to have more batteries and more PV and reduce the cost of the diesel generator? Yes or no? And under which conditions? And this is the economical calculations that will be done in the third webinar. Okay, let's go now for configuration 5. Configuration 5 is same than configuration 4, but now we also want to get rid of the grid. So we don't want to have electricity connection at all. This can be because of economical reasons, but in general, this is not the most important reason. The most important reason is that we, in fact, want to have a milk bulking group in a place where there is not electricity grid available, right? This means we don't have other option. In this case, what we need to do is to design the system accordingly. We need more PV, we need more batteries, and then we have a solar fraction of 100%. This means the whole energy demanded by the milk tank is delivered by solar energy, and we need to have a 13 oversize so that the system can be able to cool down the milk also during rainy days, also when we are having more milk than expected, and so on. As you can imagine, the configuration 5 is the most expensive one than the others, because you need to provide security. So it's not only reducing the energy consumption, you also have to have an installation that is able to have a reliability, because you cannot afford days where you don't have so much solar energy that your milk tank is not able to cool down your milk. So this is very, very important. That's why these systems have to be designed accordingly, to fulfill the expectation of the users. So we are talking here about an off-grid solution, configuration number 5. How to design such a system, how to decide which configuration is the best and what is the business model. It is important, of course, to know what is the volume of milk that you want to cool down, right? So are we talking here about 2,000 liters? Are we talking about 3,000 liters per day, and so on? Then it is very important to know when the cooling is starting. So the time of the day is very important. It makes a difference if you are cooling down the milk in the evening or in the morning, and how early in the morning you are cooling it down. Why? Because if you are cooling down milk when you have solar radiation available, then the energy can be provided directly from solar without going through the batteries. If this is not the case, then you have to store the electricity in the batteries first, and then it is provided to the milk tank. So this makes also a difference in the design. And then you have to figure out, okay, what is my the weather factor that I want to cover. So do I want to cover just the best solar days, or do I also want to cover rainy days? And depending on this, you will have more or less PV, so to say. So I can show you here an example that I have designed for Malawi, a typical sunny day and warm day with a weather factor of 80%. So this means I want to be sure I can cover all days. So to say, when the day is like 80% of the maximum, I want to be sure I can cool down 2,000 liter milk per day without consuming electricity or diesel at all. So this is my design assumption. Based on this, I have designed a system for 2,000 liter milk with 4 kilowatt peak PV and 6 kilowatt hour useful energy of the batteries. In this case, as you see, it's a relatively small solar system. Then what we have here is the time of the day in this calculation. Then you see here the solar radiation. The ambient temperature is important because we need to calculate the COP, and based on the COP, calculate the electricity consumption from the tank. So here you have the electricity consumption from the tank. You see here 6 kilowatt. If we go here to the graph, you see this is happening at 5 o'clock in the morning. We go for up to 6 kilowatt electricity consumption, and then it goes down once the milk is already cold. Here at the same time, you see the PV generation of the PV array that we have installed. So you see everything that is below the orange line, it is delivered directly PV to the milk tank, and everything that is above has to come from the batteries. So this is how you can see how the design is done. This energy has to come from the batteries, and this energy here is covered by solar radiation directly. So you see this area is almost equal to this area, and that's why the system is in balance. The battery SOC fluctuates, from 80% goes to 0 and then to 100% at 3 o'clock, 1 o'clock in the afternoon. The batteries are already full, and then they are discharged overnight. Then the milk cooling is taking place, so the batteries are discharged. In this case, the electricity from the grid is just a little bit. I see here the solar fraction is 97%, so 98%. So it is not fully 100%, but it's okay here. Because here we are trying to get the most efficient, the most cost-efficient system. So we are just designing a system in a way that typical days are covered, and if we have a rainy day or whatever, then the rest of the electricity will come from the grid, and this is very cost efficient. Then we have here surplus energy of 3.15 kilowatt hour per day. So the PV panels have, at the end, when the batteries are charged, we have a surplus energy. The electricity consumption from the grid you see here is very, very minimal. And if this has to be diesel, then you will have here the amount of liters that you consume per day. So this is the way of doing the design of a cooling system. You calculate the thermal power, thermal energy, COP, electricity consumption, and then you more or less do a design similar to the design you do for other solar systems. So you have to figure out, okay, do I have grid or not? And based on this, you design your batteries and your PV panels. I would like to show you other options of small-scale milk cooling. So we don't necessarily need always milk tanks. Also for small scale, we can use milk cans that are in a water bath. So these milk cans are in a cold water bath, and the cold water is coming from a ice storage, which is here, which has cooling units that are running directly on solar. And these cooling units produce ice. Let me show you another picture here. So we have PV panels. PV panels are connected directly to the cooling units. They produce ice, and then you have cold water for the water bath, where you then immerse the milk cans. So this is a very nice system for on-farm cooling for small volumes. This system, for example, is for 160 liter milk per day. This is how the system looks like. So you have your PV system, charge controller, the cooling units are run with or without batteries. In this case, they produce ice, and then you have a heat exchanger to cool down the water that you have here for the milk cans. You need a secondary system to run the water pumps because this system has to have battery for sure. So this one, the batteries are optional, but this one needs a small battery. And this is also a very nice way of providing a fast cooling on farm level to farmers, so that when the milk arrives, the milk bulking group is already cold, I would say 10 degrees more or less, and this increase a lot the milk quality. So it preserves the milk quality from the very beginning, so that the milk quality has a very positive impact for the dairy plants. When you receive milk that is already cold to the milk bulking group, then the milk bulking group also has less energy consumption, of course. So everything you do on farm, you don't need to do in the milk collecting group or in the milk bulking group. Okay, so that's all from my side. I thank you a lot for your attention.